Bismillahirrahmanirrahim. I am Laika Adib from Chemistry Department ID 004. The topic of my today's presentation is infrared spectroscopy. These are the contents. What is infrared? The infrared region of electromagnetic spectrum extends from the red end of visible spectrum out to microwave region. The region includes radiation at wavelength between 0.75 and 300 microns or in wave numbers between 13,000 and 33 per centimeter. It is used in the areas of determination of molecular structure, identification of chemical species, qualitative or quantitative determination of chemical species, and in a host of other applications. The spectral region of greatest use in analytical applications for studying organic compounds is the mid-infrared region. The infrared region has been subdivided into three regions which are near infrared region, middle infrared region, and far infrared region. Near IR. The absorption observed in the near-infrared region lies between 13,000 to 400 per centimeter or overtones or combinations of the fundamental stretching bands which occur in the 3,000 to 17 per centimeter region. The bands involved are usually due to carbon-hydrogen, nitrogen-hydrogen, or oxygen-hydrogen bond stretching. The resulting bands in the near-infrared are usually weak in intensity, and the intensity generally decreases by a factor of 10 from one overtone to the next. The bands in the near-infrared are often overlapped, making them less useful than mid-infrared region for qualitative analysis. However, there are important differences between the near-infrared positions of different functional groups, and these differences can often be exploited for quantitative analysis. Mid-IR. The mid-infrared spectrum lies between 4,000 to 400 per centimeter, can be approximately divided into four regions, and the nature of a group frequency may generally be determined by the region in which it is located. The regions are generalized as follow. The XH stretching region, which is present between 4,000 to 2,500 per centimeter, the triple bond region, which is present between 2,500 to 2,000 per centimeter, the double bond region, which is present between 2,000 to 1,500 per centimeter, and at the end, the fingerprint region, which present between 1,500 to 600 per centimeter. The fundamental vibrations in the 4,000 to 2,500 per centimeter region are generally due to oxygen-hydrogen, carbon-hydrogen, and nitrogen-hydrogen bond stretching. Oxygen-hydrogen stretching produces a broad band that occurs in the range 3,700 to 3,600 per centimeter. For IR, the far-infrared region is defined as the region between 400 and 100 per centimeter. This region is more limited than the mid-infrared for spectral structure correlations, but does provide information regarding the vibrations of molecules containing having atoms, molecular skeleton vibrations, molecular torsions, and crystal lattice vibrations. Intramolecular stretching modes involving heavy atoms can be helpful for characterizing compounds containing halogen atoms, organometallic compounds, and inorganic compounds. Skeletal bending modes involving an entire molecule occur in the far infrared for molecules containing heavier atoms because bending modes are usually no more than one half of the wave number of the corresponding stretching mode. Torsional modes arise because the rotation about single bonds is not free. As a result, when certain small groups are bonded to a large group, they undergo a motion with respect to the heavier anchor group. Crystal lattice vibrations are associated with the movement of whole molecular chains with respect to each other in crystalline solids. In this diagram, we can see the different regions of the infrared region. 0.7 to 2.0 region shows the near IR region, and 2.0 to 4.0 shows the medium IR region, and 4.0 to 1000 region is the far infrared region, and the wavelength is in the form of microns. Identification rules. There are a few general rules that can be used when using a mid-infrared spectrum for the determination of a molecular structure. The following is a suggested strategy for spectrum interpretation. Look first at the high wave number end of the spectrum greater than 1500 per centimeter and concentrate initially on the major bands. For each band, shortlist the possibilities by using a correlation chart. Use the lower wave number end of the spectrum for the confirmation or elaboration of possible structural elements. Do not expect to be able to assign every band in the spectrum. Keep cross-checking wherever possible. For example, an aldehyde should absorb near 1730 per centimeter and in the region 2900 to 2700 per centimeter. Exploit negative evidence as well as positive evidence. For example, if there is no band in the 1850 to 1600 per centimeter region, it is most unlikely that a carbonyl group is present. Band intensities should be treated with some caution. Under certain circumstances, they may vary considerably for the same group. Take care when using small wave number changes. These can be influenced by whether the spectrum was run as a solid or liquid or in solution. If in solution, some bands are very solvent sensitive. Do not forget to subtract solvent bands if possible. These could be confused with bands from sample. And in this diagram, we can see the different bond stretchings are present at different regions of the spectrum. For example, oxygen hydrogen bond stretching is present between the 32 to 3400 per centimeter region, and the carbon hydrogen bond stretching is present between 2850 to 3100 per centimeter region, and the carbon triple bond nitrogen or carbon triple bond carbon is present between 21 to 22.6 per centimeter region, and the 1650 to 1800 per centimeter region shows the carbon double bond oxygen stretching band, and at the end the 500 to 1000 per centimeter region shows the fingerprint region. Dipole moment changing. To absorb IR radiation, a molecule must undergo a net change in dipole moment as it vibrates or rotates. Only under these circumstances can the alternating electric field of the radiation interact with the molecule and cause changes in the amplitude of one of its motion. If the frequency of the radiation exactly matches the natural vibrational frequency of the molecule, absorption of the radiation takes place that produces a change in the amplitude of the molecular vibration. Similarly, the rotation of asymmetric molecules around their centers of mass results in periodic dipole moment fluctuations that allow interaction with the radiation field. No net change in dipole moment occurs during the vibration or rotation of homonuclear species such as oxygen, nitrogen, or chlorine. As a result, such compounds cannot absorb IR radiation. With the exception of a few compounds of this type, all other molecular species absorb IR radiation. In this diagram, the dipole moment between different atoms, for example, at the left side, the first picture shows the dipole moment is zero because it is a nonpolar molecule, and the nonpolar covalent bond has the electronegativity difference between the 0 to 0.04, and the dipole moment is zero here. In the middle diagram, the dipole moment is present and the electronegativity difference is 0.4 to 2.0, and there is one atom is partially positively charged and other is partially negatively charged. But at the right side of the diagram we can see the high dipole moment, because this molecule is highly polar in nature because of the small size of the positively charged atom and the negative size of the and the large size of the negatively charged atom, and it is basically an ionic bond, and the electronegativity difference is greater than 2.0. Stretching vibrations. There are two types of stretching vibrations: symmetrical and asymmetrical. Symmetrical stretching vibration involves similar bonds attached to a common atom in which the bonds move away and toward the common atom in unison. In asymmetrical stretching vibration, similar to symmetric stretching vibration, but one or more of the bonds move away from the common atom while the other moves towards it. And in this diagram, we can see the movement of the atoms which are shown by the arrows. In the left side of the picture, we can see the symmetrical stretching. Here arrows are towards the common atom, which show that both move towards the common atom. And if both arrows are if the head of the both arrows are away from the common atom, it shows that they simultaneously move away from the common atom. But in the case of asymmetrical stretching, we can see that one is moved towards the common atom but other is moved away from the common atom, and these are shown by the arrowhead. Bending vibrations. There are different kinds of bending vibrations. For example, scissoring. The bonds move back and forth with the deformation of the valence angle, but the atoms remain in the same plane. The motion is similar to swinging both outstretched arms straight up toward the head and back, with the body as the common atom and the arms representing bonds. The vibrational mode is also called in-plane bending. Rocking the bonds swing right and left in unison while the atoms remain in the same plane. But twisting and wedging move out of plane. Twisting. The bonds twist out of plane around a common atom, and in wedging the bonds swing back and forth in unison and out of the plane of the bond. Skeletal vibrations, these involve motion of the entire molecule. Absorption due to these vibrations occur between 1420 and 666 per centimeter or 7 to 15 micrometer. Generally, it takes more energy to stretch a bond than to bend one. Thus, stretching vibrations normally occur at higher frequencies and appear mostly in the left side of the infrared spectrum. And this diagram shows the movement of atoms in plane or out of the plane. Instrumentation of IR, and basically this is the main part of the today's presentation. In this picture we can see there is required a IR source which produces a light and falls on it, on the prisms, and there is a sample cell and reference cells. We use two kinds of cells, sample cell and reference cells, and it is called the monochromatic system. And then at the end, the light moves toward the splitter, which splits the light and the light which we want to detect goes towards the detector, and at the end we get a graph, and through this graph we can interpret the functional groups of different molecules. IR sources. IR sources consist of an inert solid that is heated electrically to a temperature between 1500 and 2200 K. These sources produce continuum radiation approximating that of a black body. The maximum radiant intensity at these temperatures occurs between 5000 and 5900 per centimeter, or 2 to 1.7 micrometer. At longer wavelengths, the intensity falls off smoothly until it is about 1% of the maximum at 670 per centimeter or 15 micrometer. On the shorter wavelength side, the decrease is much more rapid, and a similar reduction in intensity is observed at about 10,000 per centimeter or 1 micrometer. There are different kinds of IR sources. First one is the Nernst Glober. The Nernst Glober is composed of rare earth oxides formed into a cylinder having a diameter of 1 to 3 millimeter and a length of 2 to 5 centimeter. Platinum leads are sealed to the ends of the cylinder to permit electrical connections to what amounts to a resistive heating element. As current passes through the device, its temperature increases to between 1200 K and 2200 K. The nurse clover has a large negative temperature coefficient of electrical resistance, and it must be heated externally to a dull red heat before the current is large enough to maintain the desired temperature. Because the resistance decreases with increasing temperature, the source circuit must be designed to limit the current, or the glower rapidly becomes so hot that it is destroyed. The glober. A glober is a ceramic rod, usually silicon carbide or a composite material, electrically heated to more than 1000 K. Older dispersive instruments used globers that were heated as high as 1500 K to provide sufficient intensity. The sensitivity of modern FTIR instruments has meant that lower source temperatures 1000 to 1300 K can be used, resulting in longer source lifetimes. Global sources for FTIR must be temperature controlled for high stability. Some simple sources in older instruments used a fan to provide air cooling, but water cooling is more effective. The glober has the advantage of a positive temperature coefficient of resistance that makes it possible to control temperature electronically. The most stable sources therefore use electronic temperature control, which eliminates the inconvenience and temperature fluctuations of circulating water. Electronic temperature control is also said to increase the source lifetime. Comparison. There is a comparison between the glober and nurse glober. Spectral energies of the glober and nurse glober are similar except in the region below 5 micrometer, where the glober is significantly more intense. Spectral energies of the glober and nurse glober are comparable except in the region below 505 micrometer, where the glober provides a significantly greater output. At the right side of the diagram is the nurse glober, and the sorry, the left diagram shows the nurse glober, and the right diagram is the glober. Incandescent wire source. A source with somewhat lower intensity but with longer life than the glober or nurse glober is a tightly wound spiral of nichrome wire heated to about 1100 K by an electrical current. A rhodium wire heated sealed in a ceramic cylinder has similar properties, although it is more expensive. Nichrome wire sources are less intense than many IR sources. However, the incandescent wire source requires no cooling and is nearly maintenance free. For this reason, the nichrome wire source is often used where reliability is paramount, such as in process analyzers. And in this diagram, we can see there at the bottom side there is an electrical foot contact, and the insulation is present here, and the screw thread contact is also present. There is a glass mount, and the whole structure is in the form of bulb, and the inert gas is used in this bulb, and there are also present sport wires. The mercury arc. For the 4IR region of the spectrum 1.50 micrometer, none of the thermal sources just described provide sufficient radiant power for the convenient detection. In this region, a high pressure mercury arc is often used. This device consists of a quartz jetted tube containing mercury vapor at a pressure greater than 1 atmosphere. When an electric current passes through the vapor, an internal plasma source is formed that provides continuum radiation in the 4IR region. And in this diagram it shows the mercury arc, and in this diagram we can see it is in the form of glass envelope. At the left side there is an anode lead, and it acts at anode. There is arm also present, and at the bottom side excitation electrode is present, and the liquid mercury cathode is present at the bottom side. And the lead cathode is also present, and there is an ignition anode. Means there are three kinds of anode: lead anode, simple anode, and ignition anode. And there are two types of cathode: liquid mercury cathode and the lead cathode. The tungsten filament lamp. An ordinary tungsten filament lamp is a convenient source for the near IR region of 4000 to 12,800 per centimeter, or 2.5 to 0.78 micrometer. It has long life of about 1200 hours. And in this diagram, we can see the construction of tungsten filament lamp. There is a spider which is present at the upper side, and lead is present in wires, and the at the bottom side there is a beyond cap, and at the middle side there is a fuse, and glass stream is also present, and at the upper side there is a tungsten filament. The carbon dioxide laser source. A tunable carbon dioxide laser is used as an IR source for monitoring the concentrations of certain atmospheric pollutants and for determining absorbing species in aqueous solutions. A carbon dioxide laser produces a band of radiation in the range of 900 to 1100 per centimeter, or 11 to 9 micrometer, which consists of about 100 closely spaced discrete lines. This source is useful for quantitative determination of a number of important species such as ammonia, butadiene, benzene, ethanol, nitrogen dioxide, and trichloroethylene. Carbon dioxide lasers are widely used in remote sensing applications such as light detection and ranging. This is the construction of carbon dioxide laser source. The laser beam is used in this medium. There is a stimulated emission, and there are two types of mirrors present. One mirror is output mirror, and other is the rear mirror. And the blue area shows the excitation, and the active medium, and it is basically the active medium where the excitation occur. And the pink area is the stimulated emission area. Semiconductor IR laser sources. Tunable semiconductor lasers have also been used as sources in the near and mid IR regions. As an example, the sample analysis at Mars SAM experiment on the Mars rover Curiosity Science Laboratory uses a tunable diode laser spectrometer in the 2.78 micrometer region to detect carbon, hydrogen, and oxygen in the Martian environment and to determine their isotopic ratios. A quantum cascade tunable laser is used to detect methane by scanning across several of its rotational lines in the 3.3 micrometer region. Methane is determined by the difference in the absorption signals obtained from a closed sample cell filled with the Mars atmosphere and the same cell evacuated by means of a turbomolecular pump. Wavelength selector. Wavelength selectors limit the radiation absorbed by a sample to a certain wavelength or a narrow band of wavelengths. There are two types of wavelength selectors. First one is filters and other is monochromator. Filters. Filters are used to remove the unwanted wavelength or it will allow only a particular wavelength to pass through the sample. It should have high transmittance at the desired wavelength. It should have low transmittance at the other wavelength. Absorption filter and interference filters. These are the different kinds of filters that is used in the laboratories. And the diagram B and C shows the different graphs which we obtained by using different filters. Absorption filter, commonly used in visible spectrophotometer, normally constructed of colored glass, colored films, or a dye in a gelatin. Often two absorption filters are paired to give a narrower band of transmittance. Selectively depends on the thickness of the glass, less degree of monochromaticity, hence used only for simple photometers. Gelatin filters consist of mixture of dyes placed in gelatin and sandwiched between glass plates, and the bandwidth is 25 nanometer. Glass filters, these made from piece of colored glass which transmits limited wavelength range of spectrum, color produced by incorporation of oxides of vanadium, chromium, iron, nickel, and copper. And in this diagram is a glass filter correlation spectrometer which is used in the laboratories. The light sources came and there is a rotating filter wheel which is filled with interest of gas, and there is also a non-specific filter, and then light move towards the sample gas. There are two holes, which one is used as the inner input sample gas, and the other hole is used as the gas sample output. And at the end, the left light is moved towards the detectors which detects the spectra. Interference filters, it consists of two semi-transparent layers of silver deposited on glass by the process of evaporation in vacuum, and they are separated by a layer of dielectric. Useful in the UV, visible, and IR regions of the EM spectrum. And in this diagram, we can see at the right side the spectra which we gain from the interference filters, and at the left side there are we can see multiple reflections in air are used, and we use high reflectance mirrors. Interference wedges, if two glass plates are placed face to face with one end separated by a piece of tissue paper or thin metal foil, on air wedge will be formed between them. If monochromatic light is directed on the plates, a series of straight line fringes will be seen parallel to the line along which they touch. This is due to interference by division of amplitude, as with Newton's rings. Some light is reflected from the bottom surface of the top plate and some from the top surface of the bottom plate. And here we can see the incoming beam light, and at the bottom the outgoing beam light. And there are two types of reflections. The blue reflection is the reflection 1 and the purple shows the reflection 2. And the yellow arrow shows the absorption at the bottom side. The anti-reflectance coating layer thickness is shown by lambda over 4, and the destruction interference is shown by lambda over 2. Monochromators. The radiation source emits radiation of variable frequencies, but the sample in the IR spectroscopy absorbs only at certain frequencies. It is therefore necessary to select desired frequencies from the radiation source and reject the others. The selection has been achieved by means of monochromators. The prism or grating type monochromators are employed in the infrared world. However, prism instruments are favored because of greater range and simplicity. It is of two types: prism monochromator and diffraction grating monochromator. Components of monochromator. First one is entrance slit. It provides a rectangular optical image of the incoming polychromatic radiation. Collimating lens or mirror provides a parallel beam of radiation that impinges upon the dispersive element. Prism or grating disperse the polychromatic radiation by the process of diffraction. Focusing lens or mirror focuses the dispersed radiation on the exit slit, and the exit slit which isolate the wavelength band of interest. Prism monochromator. The prism reflects light into its different colors or into at different wavelengths. The dispersion occurs because the angle of refraction is dependent on the refractive index of the prism's material, which in turn is slightly dependent on the wavelength of light that is traveling through it. And in this diagram we can see the incident light is passed through the prism, and then it is converted into reflecting light and reflect at different wavelength, and the different wavelength shows the different colors. Grating monochromator. A monochromator is an optical instrument which measures the light spectrum. Light is focused in the input slit and is diffracted by a grating. In this way, only one color is transmitted through the output slit at a given time. Spectra are then recorded in wavelength by wavelength rotating the grating. Gratings can be reflective or transmissive, and the surface of a grating can either be planar or concave. Planar gratings generally give higher resolution over a wide wavelength range, while concave gratings can function as both a dispersing and focusing element in a spectrometer. A grooved or blazed mirror that has relatively broad faces upon which reflection occurs and narrow unused faces. Grating has higher dispersion than prism, and it follows the laws of diffraction. N lambda is equal to d into sine I plus negative sine theta. N is in order of grating, lambda is the wavelength of the radiation, d is the distance between the grooves, I is the angle of incidence, and the theta is the angle of dispersion. And here we can see in this diagram the monochromatic wave is came, and after passing through the monochromatic slit, it dispersed or diffracted at different wavelengths and produces a light with different wavelengths. Detectors. Detectors are the devices that convert the radiation to an electrical signal. There are some properties of of an ideal detector, which are these are highly sensitive, high signal to noise ratio, constant response over a large range of wavelengths, forced response time. Electrical signal produced is proportional to the radiant power. S is equal to kp. S shows the electrical signal, P shows the radiant power, and K is the calibration sensitivity. Types of IR detectors. There are three categories of IR detectors: thermal detectors, Gole cell or pneumatic detectors, and photoconductive detectors. The thermal detectors are subdivided into different types, which are thermocouples, thermistors, bolometer, and pyroelectric transducers. Thermal detectors. Thermal transducers whose responses depend on the heating effect of the radiation are found in older dispersive spectrometers for detection of all but the shortest IR wavelengths. The radiation is absorbed by a small black body and the resultant temperature rise is measured. The radiant power level from a spectrophotometer beam is minute, between 1027 to 1029 volt, so that the heat capacity of the absorbing element must be as small as possible if a detectable temperature change is to be produced. Under the best of circumstances, temperature changes are confined to a few thousandths of a Kelvin. The problem of measuring IR radiation by thermal means is compounded by thermal noise from the surroundings. Thermocouples. In its simplest form, a thermocouple consists of a pair of junctions formed when two pieces of a metal such as bismuth are fused to each end of the dissimilar metal such as antimony. A potential difference between the two junctions varies with their differences in temperature. The transducer junction for IR radiation is formed from very fine wires or alternatively by evaporating the metals onto a non-conducting spot. The junction is usually blackened to improve its heat absorbing capacity and sealed in an evacuated chamber with a window that is transparent to IR radiation. The response time is typically about 30 milliseconds. And here is the construction of thermocouples. They use a voltmeter, and at the left side we use a heat source which measure, and it is also called the measuring junction, and at the left side is the reference junction which is cold in nature, and there are two wires are used which are made up of dissimilar metals. Bolometers. A bolometer is a type of resistance thermometer constructed of strips of metal such as platinum or nickel or from a semiconductor. This type of semiconductor device is sometimes called a thermistor. Semiconductor materials exhibit a relatively large change in resistance as a function of temperature. The responsive element in a bolometer is kept small and blackened to absorb the radiant heat. Bolometers are not extensively used as other IR transducers for the mid-IR region. However, a germanium bolometer operated at 1.5 K is an excellent transducer for radiation in the range of 5 to 400 per centimeter or 2000 to 25 micrometer. And the resume time is a few milliseconds. And here is the construction of bolometers. There is a thermal bath which is represented by T naught, and at the middle there are thermal links which links the both, and there is also use a thermosensor, and in the diagram we can see there is a absorber, and delta D shows the differences, and the particle energy is released is shown by E. Thermistors. Thermistor is a resistance thermometer or a resistor whose resistance is dependent on the temperature. And these are the different kinds of thermistors that are used in the market. Pyroelectric detectors. The pyroelectric detectors are constructed from single crystalline wafers of pyroelectric materials which are insulators or dielectric materials with very special thermal and electrical properties. Triglycine sulfate, sulfuric acid, usually deuterated DTGS, and often with a fraction of glycines replaced with alanine. DLATGS is the most important pyroelectric material used for IR detection systems. When an electric field is applied across any dielectric material, polarization takes place, with the magnitude of the polarization being a function of the dielectric constant of the material. Pyroelectric substances retain a strong temperature-dependent polarization after the removal of the field. The magnitude of this current is proportional to the surface area of the crystal and the rate of change of polarization with temperature. Photoconducting transducers. IR photoconducting transducers consist of a thin film of a semiconductor material such as lead sulfide, mercury telluride, cadmium telluride, or indium antimonide deposited on a non-conducting glass surface and sealed in an vacuum envelope to protect the semiconductor from the atmosphere. Absorption of radiation by these materials promotes non-conducting valence electrons to a higher energy conducting state, thus decreasing the electrical resistance of the semiconductor. A lead sulfide photoconductor is the most widely used transducer for the near IR region of the spectrum from 10,000 to 333 per centimeter or 1 to 3 micrometer. It can be operated at room temperature. For mid and for IR radiation, MCT photoconductor transducers are used. They must be cooled with liquid nitrogen at 77 K to minimize thermal noise. Goalie cell. The Goalie cell is a type of optoelectric detector mainly used for infrared spectroscopy. It consists of a gas-filled enclosure with an infrared absorbing material and a flexible diaphragm or membrane. When infrared radiation is absorbed, it heats the gas, causing it to expand. The resulting increase in pressure deforms the membrane. Light reflected off the membrane is detected by a photodiode, and motion of the membrane produces a change in the signal on the photodiode. And in this diagram, we can see there are the IR windows at the left side, and the glass filled cavity contains an IR absorber, and at the bottom side there is a compensation leak, and in the right side we can see there is a membrane, and the whole system is called housing, and there are optical reader system are used. Mid IR spectrometry. Mid-IR absorption and reflection spectrometry are major tools for determining the structure of organic and biochemical species. And in mid-IR spectrometry, there are different kinds of sample handling techniques which we use. Sample handling is frequently the most difficult and time-consuming part of an IR spectrometric analysis. There are different kinds of samples which we have to handle during the process. The first one is the gases. The spectrum of a low boiling point liquid or a gas can be obtained by permitting the sample to expand into an evacuated cylindrical cell equipped with suitable windows. For this purpose, a variety of cylindrical cells are available with path lengths that range from a few centimeters to 10 meter or more. The longer path lengths are obtained in compact cells by providing reflecting internal surfaces so that the beam makes numerous passes through the sample before exiting the cell. And in this diagram, there is a lamp house and signals are under control. I naught shows the intensity, and IT shows the intensity of the target gas, and the concentration of the gas is shown by capital C, and the gas is entered from the upper side and the gas is exported from the lower side, and the detectors are present at the right side, and the output is equal to U directly proportional to IT. Liquids. When the amount of a liquid sample is small or when a suitable solvent is unavailable, it is common practice to obtain spectra on the pure liquid. The thickness of a very thin film of liquid parents are sufficiently presents a sufficiently short path length to produce satisfactory spectra. Commonly, a drop of the neat liquid is squeezed between two salt plates to give a layer 0.015 millimeter thick or less. The two plates held together by capillary action and then placed in the beam path. This technique does not give particularly reproducible transmittance data, but the resulting spectra are usually satisfactory for qualitative investigations. And in this diagram, at the left side are the liquid holders which are used, and we can see there is a dropper which drops the liquid on the liquid holder, and at the end the detection is occur, and we got this kind of spectra. Solids. Most organic compounds exhibit numerous absorption bands throughout the mid-IR region, and finding a solvent that does not have overlapping bands is often impossible. Because of this, spectra are often obtained on dispersion of the solid in a liquid or solid matrix. Generally, in these techniques, the solid sample must be ground until its particular size is much less than the wavelength of the radiation to avoid the effects of the scattered radiation. In this solid sample handling, there are different techniques are used. First one is the paletting. One of the most popular technique for handling solid samples has been KBR paletting. Other alkali metal halides have also been used. Halide salts have the property of cold flow, in which they have glass-like transparent or translucent properties when sufficient pressure is applied to the finely powdered materials. In using this technique, a milligram or less of the finely ground sample is intimately mixed with about 100 milligram of dried spectroscopic grade potassium bromide powder. Mixing can be carried out with the mortar and pestle or better in a small ball mill. The mixture is then pressed in a special die at 10,000 to 15,000 pounds per square inch to yield a transparent disc. Best results are obtained if the disc is formed in a vacuum to eliminate occulted air. The disc is then held in the instrument beam for spectroscopic examination, and the resulting spectra frequently exhibit band at 3450 and 1640 per centimeter or 2.9 to 6.1 micrometer due to absorbed moisture. And there are the assembly of the KBR pallets, and the instrument is like this that is present at the right side. Nodule mull. Nodule is selected as a mulling agent since it is a mixture of high molecular weight hydrocarbons exhibiting only a few absorption bands, resulting mainly from carbon-hydrogen bond stretching and bending vibrations. In preparing a nodule mull, approximately 4 to 6 milligrams of the dry sample is ground to a fine powder, preferably using the smooth surface of an agate mortar and pestle. A drop of nodule or mineral oil is added to the powder sample, and the grinding continued until a thick paste is obtained. A thin film of the paste is spread between the two plates and the spectrum obtained. The particular size of the finished sample and the thickness of the nodule mold between the plates are important factors in obtaining a satisfactory spectrum. If the film is too thick, the light will not be adequately transmitted through the sample, and if it is too thin, the spectrum will consist mostly of nodule bands. By rotating the salt plates against each other, a thick sample may be thinned sufficiently to give a satisfactory spectrum. Even a good spectrum will show absorption due to the mulling agent. And by using a mulling agent, we can get this kind of spectrum. Other methods for solids, the IR behavior of solids can also be obtained by casting a thin film of the sample as is done with many polymers. For some samples, spectra can be acquired by reflectance techniques, and by the photoacoustic method, these spectra are often similar to absorption spectra and provide the same kinds of information. Software for IR. Opus is the leading spectroscopy software for state-of-the-art measurement, processing, and evaluation of IR, NIR, and Raman spectra. Opus base package includes a wide range of functionality for various types of measurements, data processing and evaluation. Up-to-date 3D and video software packages provide state-of-the-art workflows for microscopy and imaging applications, including comfortable analysis and visualization functions. For example, also relevant for time-resolved spectroscopy data for inline process applications. The CMET software package was in particular optimized for high stability and availability in demanding production environments. Moreover, Broker also offers a dedicated software package for the time-dependent monitoring of chemical reactions. Agilent Microlab Expert is an advanced FTIR spectroscopy software that provides a new level of flexibility and spectral visualization for Agilent FTIR spectrometers. This state-of-the-art software designed is for use when spectral visualization and data processing are required to tackle sophisticated analytical challenges. Microlab Expert provides the advanced user spectral visualization tools, data manipulation and processing capabilities that are critical in order to support methods development, IR interpretation, organic synthesis, and R&D and non-routine lab work. Microlab Expert provides an ideal balance between ease of operation and sophisticated data handling. It is the construction of the Microlab Expert, and we can get this kind of graph by using a Microlab Expert, and the instrumentation is like this. Manufacturer companies of fire instruments in worldwide, these are the different companies which are used worldwide for the manufacturing of the instruments that are used during the infrared spectroscopy. Types of instruments. Three types of instruments for IR absorption measurements are commonly available: dispersive spectrophotometers with the grating monochromator, FT spectrometers employing an interferometer, and non-dispersive spectrophotometers using a filter or an absorbing gas that are used for analysis of atmospheric gases at specific wavelengths. Until the 1980s, the most widely used instruments for IR measurements were dispersive spectrophotometers. Now, however, this type of instruments has been largely displaced for mid and for IR measurements by FT spectrometers because of their speed, reliability, signal to noise advantage, and convenience. Dispersive spectrometers are still used in the near IR where they are often extensions of UV visible instruments, but many dedicated near IR instruments are of the Fourier transform IR, means FTIR type. FTIR spectrophotometers. Fourier transform infrared spectrometer obtains an infrared spectra by first collecting an interferogram of a sample signal using an interferometer, then performs a Fourier transform on the interferogram to obtain the spectrum. An interferogram is an instrument that uses the techniques of the superimposing, means interfering two or more waves to detect the differences between them. The FTIR spectrometer uses a Michelson interferometer. The heart of the FTIR is a Michelson interferometer. The mirror moves at a fixed rate. Its position is determined accurately by counting the interference fringes of a collected helium neon laser. The Michelson interferometer splits a beam of radiation into two parts having different lengths and recombines them. Our detector measures the intensity variations of the exit beam as a function of the path difference. A monochromatic source would show a simple sine wave of intensity at the detector due to constructive and destructive interference as the path length changes. In the general case, superstitions of wavelengths enter spectrometer and the detector indicates the sum of the sine waves added together, some idealized light sources, and the interferogram that they would theoretically produce. The difference in the path length for the radiation is known as the retardation. When the retardation is zero, the detector sees a maximum because all the wave numbers of the radiation add constructively. When the retardation is 1 over 2, the detector sees a minimum for the wavelength 1, and interferogram is the sum of all the wave number intensities. FT spectrometers. In FT spectrometers, coding is accomplished by splitting the source into two beams whose path lengths can be varied periodically to give interference patterns. The FT is then used for data processing. The second is Hammad transform spectrometer, which is a dispersive instrument that uses a moving mask at the focal plane of the monochromator for encoding the spectral data. Hadamard transform IR instruments have not been widely adopted. When FTIR spectrometers first appeared in the marketplace, they were bulky, expensive, and required frequent mechanical adjustments. FT instruments have now been reduced to benchtop size and have become reliable and easy to maintain. Furthermore, the price of the simple models has been reduced to the point where they are competitive with all but the simplest dispersive instruments. FT instruments have largely displaced dispersive instruments in the laboratory. FTIR instrument design. FTIR spectrometer can be single or double beam instruments. Single beam FTIR. A typical procedure for determining transmittance or absorbance with this type of instruments is to first obtain a reference interferogram by scanning a reference 20 or 30 times, co-adding the data and storing the results in the memory of the instrument computer. A sample is then inserted in the radiation path and the process repeated. The ratio of the sample and the reference spectral data is then computed to give the transmittance at various frequencies. From this ratio, the absorbance is calculated as a function of wave number. And in this diagram, we can see light comes from a source of light, and there is one monochromatic which splits the light, and spectrum of light is obtained. There is a light is absorbed by a sample, and then there are detectors which detect the signals, and at the end there is an amplifier which amplifies the signals, and at the end we get the value. Double beam. In a double beam spectrometer mirrors detecting the interferogram beam through the sample, and reference cells are oscillated rapidly compared to the movement of the interferometer mirrors, so that sample and reference information can be obtained to each mirror position. The double beam design compensate for source and detector drifts. And in this diagram, we can see the light is came from the light source, and there is a monochromator and which produces a spectrum of light which passes through the prism. And there are two types of cells are used. First one is the reference cell and the other is the sample cell. There is light absorbed and then passed through the photocell detectors. At the end, there is a amplifier which detects the signals, and at the end we get the value. Performance characteristics of commercial instrument. A number of instrument manufacturers offer several models of FTIR instruments. The least expensive has a range of 7800 to 350 per centimeter, or 1.3 to 29 micrometer, with a resolution of a few wave numbers. This performance can be obtained with a scan time as brief as 1 second. More expensive instruments with interchangeable beam splitters, sources and transducers offer expanded frequency ranges and high resolutions. For example, one instrument is reported to produce spectra from the far IR 10 per centimeter or 100 micrometer through the visible region to 50,000 per centimeter or 200 nanometer. Advantages of FTIR. FTIR instruments have advantages over dispersive instruments in all areas of chemistry, particularly for very high resolution work that is encountered with gaseous mixtures having complex spectra resulting from the superposition of vibrational and rotational bands, the study of samples with high absorbance, the study of substances with weak absorption bands, for example, the study of compounds that are chemisorbed on catalyst surfaces, investigations requiring fast scanning such as kinetic studies or detection of chromatographic effects, collecting IR data from very small samples, obtaining reflection spectra, and IR emission studies. The other type of IR instrument is a dispersive instrument. Although nearly all instruments produced today are FT systems, when dispersive spectrophotometers are still found in laboratories. Dispersive IR spectrophotometers are generally double beam recording instruments which use reflection grating for dispersing radiation. The double beam design is less demanding with respect to the performance of sources and detectors. An important characteristic because of the relatively low intensity of IR sources, the low sensitivity of IR transducers, and the resulting requirement for large signal amplifications. And in this diagram, we can see the infrared energy sources used, and there are the sources pass through the different mirrors, and there is a reference cell and sample cell, and there is also present a motor and the light is passed through the beam chopper, and and there are different mirrors are also present at different sides. Then it passed through the diffraction grating which diffract the light into at different angles, and there are different two types of slits are used which slit the light towards the detector, and at the end the light is detected while passing through the applications, and at the end we get the record or spectra from the recorder. Non-dispersive infrared spectroscopy. Non-dispersive infrared spectroscopy or NDIR is often used to detect gas and measure the concentration of carbon oxides, for example, carbon monoxide or carbon dioxide. An infrared beam passes through the sampling chamber, and each gas component in the sample absorbs some particular frequency infrared. In parallel, our reference gas, typically nitrogen, is used in another chamber. By measuring the amount of absorbed infrared at the necessary frequency, the concentration of the gas component can be determined. It is called non-dispersive because the wavelength which passes through the sampling chamber is not pre-filtered, and instead the optical filter is in front of the detector to eliminate all light except the wavelength which selected gas molecules can absorb. Now the applications of the IR. First one are the biological applications. Nucleic acid. Nucleic acids are vital molecules which carry the genetic code and are responsible for its expression by protein synthesis. Deoxyribonucleic acid and ribonucleic acid may be studied by using infrared spectroscopy. The spectra of nucleic acid may be divided into the modes due to constitute base, sugar, and phosphate groups. Bands in the 1500 to 1250 per centimeter region of nucleic acid are due to the vibrational coupling between a base and a sugar, and in the region 1250 to 1000 per centimeter range, sugar phosphate chain vibrations are observed. Disease diagnosis. In recent years, infrared spectroscopy has emerged as a powerful tool for characterizing tissue and disease diagnosis. The pressure dependence or parameters such as wave number, intensity, and band shape may provide further information about the structural changes associated with malignancy. For example, it is possible to detect cervical cancer arising from a pre-malignant state termed dysplasia by using infrared band differences among normal dysplastic and malignant cervical cells. A study of the pressure dependence of the wave number of bands indicates that there are extensive changes in the degree of hydrogen bonding of phosphodiester groups of the nucleic acid and the carbon hydroxyl groups of the proteins. Lipids. Infrared spectroscopy can provide valuable structural information about lipids, which are important molecular components of membranes. Lipids are organized in bilayers of about 40 to 80 angstrom in thickness, where the polar head group points towards the aqueous phase and the hydrophobic tails point towards the tails of a second layer. The chains can be in an all trans conformation, which is referred to as the gel phase, or a liquid crystalline phase is obtained when the chain also contains gauge carbon bond groups. The infrared spectra of phospholipids can be divided into spectral regions that originate from the molecular vibrations of the hydrocarbon tail and the interference region and the head group. Plants. The infrared analysis of the plant material has traditionally relied upon the use of harsh chemicals and the modification of the intractable cell walls. Plants comprise up to 80% of the dry weight of carbohydrates, with the most important including cellulose, starch, pectins, and sugars such as glucose and sucrose. The advent of FTIR microspectroscopy has allowed for the investigation of localized regions of plant cells. Infrared microscopy can be used to compare an old plant with a young plant. Now, industrial and environmental applications of IR. Pharmaceutical industry. Infrared spectroscopy has been extensively used in both qualitative and quantitative pharmaceutical analysis. This technique is important for the evaluation of the raw material used in production, the active ingredient, and the excipients. Nuclear magnetic resonance spectroscopy and mass spectrometry are widely used in the pharmaceutical industry for the identification of drug substances. Infrared spectroscopy can provide valuable additional structural information such as the presence of certain functional groups, the presence of oxygen hydrogen groups in acid, aceta- acetyl salicylic acid is indicated by a broad band in the 3400 to 3300 per centimeter region. Carbon hydrogen bond strength bands overlap with this band in the 3000 to 2800 per centimeter range. Food sciences. Both mid-infrared and near-infrared techniques may be used to obtain qualitative and quantitative information about food samples. Infrared spectroscopy has long been employed to study fats and oils. One important infrared method is the determination of trans isomers in fats and oils. NIR spectroscopy has been used for many years in the dairy industry to examine milk. Wine analysis is also feasible with near infrared spectroscopy. Other alcoholic beverages, including beers and spirits, can be analyzed by using NIR spectroscopy. Agriculture applications. Commercial grains are commonly analyzed by using the major constituents of grains or water, protein, oil, fiber, minerals, and carbohydrates, and it is commercially important to quantize the composition. NIR spectra of such materials are thus dominated by the overtones and combination bands of carbon, hydrogen, nitrogen, hydrogen, oxygen, hydrogen, and carbon double bond oxygen bonds. Pulp and paper industry. Infrared spectroscopy plays an important role in the quality control in the pulp and paper industries. Paper is comprised of cellulose fibers, inorganic fillers, and binders. In the mid infrared region, additives such as polymers and calcium carbonate may be identified in paper. The majority of bands in a paper spectrum are due to cellulose. Environmental applications. Infrared spectroscopy has been applied to a broad range of environmental sampling problems, including air, water, and soil analysis. The development of remote sensing infrared techniques has been particularly useful in this field, and simple practical infrared techniques have been developed for measuring trace gases and atmospheric compositions. Determination of the composition of atmospheric gases is important for an understanding of global climate changes, and infrared spectroscopy can be used for measuring the most abundant and more important greenhouse gases. Thank you.